Every kid has dreamed of digging to China, but in 2025, we finally have the technology to find out how close we could actually get. With diamond-tip drill bits that can pulverize granite and automated drilling systems that operate continuously without human intervention, modern engineering has solved problems that seemed impossible just decades ago. Russia's Kola Superdeep Borehole reached 12,262 meters down, deeper than the Mariana Trench is deep, before extreme conditions force them to stop. But here's what nobody talks about. There's still one enemy that even our most advanced technology can't defeat. And it's waiting for us much closer to the surface than you think. To understand why, we need to start at the beginning and work our way down. Starting small, the first few meters. The first few meters beneath our feet contain the hidden infrastructure that makes modern life possible. Most people walk over this underground world without realizing that everything from their internet connection to their home's foundation exists in carefully planned layers just below the surface. At 8 meters down, we reach the standard depth for residential geothermal systems in 2025. These installations tap into the Earth's constant temperature at this depth, where the ground maintains a steady temperature regardless of surface weather conditions. In most locations, the temperature at 8 meters stays around 10 to 16 degrees Celsius year-round. Homeowners install loops of pipe at this depth to heat their houses in winter and cool them in summer. The excavation for a typical residential geothermal system creates trenches that could easily hide a single-story house. Modern metal detectors can penetrate down to similar depths, thanks to advances in electromagnetic field generation and signal processing. Professional archaeologists and treasure hunters use these devices to locate objects buried far deeper than previous generations of equipment could reach. The electromagnetic field generated by these detectors weakens with distance, but improved sensitivity allows detection of large metallic objects even at these depths. Continue down to 12 meters, and we discover the deepest recorded tree roots in urban environments. City trees face unique challenges because concrete, utility lines, and compacted soil force their roots to grow in unusual patterns. Some species have adapted by sending single roots straight down like biological drill bits, searching for water and nutrients below the urban landscape. These taproots can punch through small gaps in infrastructure and reach depths equivalent to a 4-story building. The roots at this depth are typically no thicker than a garden hose, but they can extend the tree's reach into soil layers that remain moist even during droughts. To put these depths in perspective, 12 meters equals the height of a typical 3-story apartment building. If you placed a standard city bus on its end, it would reach about 12 meters into the air. A telephone pole installed in 2025 typically stands 12 meters tall, which means our deepest tree roots extend as far underground as these poles reach above ground. A 2-story house with a standard roof peak measures roughly 8 meters from foundation to tip. So our geothermal systems extend slightly deeper than a house is tall. What makes these shallow depths remarkable is that humans could theoretically reach all of them using basic hand tools. Archaeological digs regularly reach 8 to 12 meters using nothing more sophisticated than shovels, picks, and buckets. The main limitation isn't technology, but time and effort. Professional excavation equipment makes these depths routine. A standard backhoe can easily reach 8 meters, while larger excavators extend to 12 meters or more. Construction crews dig to these depths daily for building foundations, utility installations, and infrastructure projects. The ground temperature at 12 meters fluctuates only slightly throughout the year, typically varying by just 2 to 3 degrees Celsius between summer and winter. This thermal stability makes these depths attractive for various applications beyond geothermal systems. Food storage facilities sometimes extend to these depths to take advantage of the natural cooling effect. Wine cellars built at 8 to 12 meters maintain consistent temperatures without mechanical cooling systems. Soil composition at these depths varies dramatically depending on location, but most areas still contain workable earth that responds predictably to excavation. Clay soils become more plastic and sticky, while sandy soils maintain their loose texture. Rocky areas present challenges, but standard construction equipment can break through most rock formations found at these shallow depths. Emergency services can easily reach accidents or cave-ins at these depths using conventional rescue equipment. fire departments carry ladders and rope systems capable of accessing 12-meter excavations. This accessibility means that construction work at these depths follows standard safety protocols without requiring specialized rescue teams on standby. Water tables in many regions exist somewhere between 5 and 12 meters, depending on local geology and seasonal rainfall. Excavations at these depths often encounter groundwater, which creates muddy conditions but rarely poses serious engineering challenges. Standard pumping equipment can handle the water infiltration typical at these levels. The air quality at 12 meters typically remains breathable without mechanical ventilation, though confined spaces require monitoring for carbon dioxide buildup and oxygen depletion. Workers can spend extended periods at these depths without specialized breathing equipment, assuming proper ventilation practices. For comparison, humans have dug much deeper by hand when necessary. The Woodingdean water well in the UK was dug entirely by hand in 1862 and reached 392 meters down. But modern drilling rigs have shattered all hand-digging records. Russia's Kola Superdeep Borehole reached 12,262 meters down using advanced drilling technology, proving that our machines can penetrate depths that would be impossible for manual excavation. These familiar depths represent just the beginning of our journey underground. The geothermal systems, tree roots, and basic infrastructure that exist in this shallow zone form part of the hidden foundation of modern life. Yet everything we've explored so far barely scratches the surface of human engineering capabilities. The natural features and simple installations at these depths seem substantial, but they represent only the most accessible layer of human construction beneath the surface. Underground landmarks we actually use. Beyond where we park cars, underground labs, and subways lie depths only machines can reach, starting at 2,197 meters, the deepest cave, and pushing further into mines and scientific boreholes. At 2,197 meters down, we encounter the Molina cave system, representing the deepest point that natural geological processes have carved into the Earth's crust. This cave system extends deeper than 7 Empire State Buildings stacked on top of each other. The cave reaches depths where atmospheric pressure increases significantly and where the temperature begins to rise noticeably due to geothermal heating. Explorers who venture into these depths require specialized equipment to manage the changing atmospheric conditions and the complete absence of natural light. The cave walls at 2,197 meters experience pressure from the weight of over 2 kilometers of rock above. This immense pressure creates geological conditions that differ substantially from surface environments. Water behavior changes at these depths, with different boiling points and flow characteristics that affect how underground rivers and pools form within the cave system. The air composition remains breathable, but the humidity and temperature create challenging conditions for human exploration. Cave exploration at these depths requires extensive logistical planning, because rescue operations become extremely complex. Emergency teams must transport equipment through narrow passages and vertical drops that extend for over 2 kilometers. The time required to evacuate an injured person from 2,197 meters underground can exceed 24 hours even with optimal conditions and experienced rescue teams. Moving deeper to 4,000 meters, we reach the operational depth of the Tautona mine in South Africa, one of the deepest mining operations on Earth. This gold mine extends so far underground that miners must travel the equivalent distance of driving from one city to another just to reach their work areas. The journey from surface to the deepest working levels takes over an hour using high-speed mining elevators. At 4,000 meters underground, the rock temperature reaches approximately 60 degrees Celsius due to geothermal heating. The mine requires massive refrigeration systems that pump chilled air through kilometers of ventilation shafts to create working conditions that humans can survive. These cooling systems consume enormous amounts of energy and represent one of the largest operational expenses for deep mining operations. The rock pressure at 4,000 meters creates conditions where tunnel walls can collapse without warning. Mining engineers install extensive support systems using steel beams, concrete reinforcement, and rock bolts that extend deep into surrounding stone. The pressure is so intense that solid rock behaves almost like a thick liquid, slowly flowing and deforming over time. Miners must constantly monitor tunnel integrity because the mountain literally tries to close the excavated spaces. Workers at these depths face unique physiological challenges beyond just heat and pressure. The human body responds differently to the atmospheric conditions found 4,000 meters underground. Blood circulation changes, and workers require acclimatization periods. Similar to high-altitude training, the mine operates with strict rotation schedules because extended exposure to these conditions affects human performance and safety. Transportation of materials to 4,000 meters requires specialized equipment capable of handling the extreme conditions. Standard construction materials behave differently under the pressure and temperature found at these depths. Steel becomes more brittle, concrete curing processes change, and electronic equipment requires additional protection from the harsh environment. The deepest point that represents the absolute limit of human engineering achievement underground is 12,262 meters, reached by Russia's Kola Superdeep Borehole. This scientific drilling project pushed deeper into the earth than any previous human construction. The borehole extends deeper than the deepest ocean trenches and represents humanity's deepest penetration into the planet's crust. The Kola project encountered conditions that challenged every assumption about deep Earth geology. At 12,262 meters, the temperature reached 180 degrees Celsius, much hotter than the expected 100 degrees Celsius that scientists had predicted. The rock at these depths behaved more like plastic than solid stone, making drilling extremely difficult. The pressure was so intense that the borehole walls constantly tried to close, requiring continuous intervention to keep the hole open. The drilling equipment used for the Kola project represented the most advanced technology available for deep earth penetration. Diamond-tip drill bits capable of cutting through the hardest rock formations wore out rapidly under the extreme conditions. The drilling fluid used to cool the equipment and remove rock debris had to be specially formulated to remain stable at temperatures that would destroy conventional materials. Communication with equipment at 12,262 meters required specialized systems because standard electronic equipment fails under the pressure and temperature conditions found at these depths. The drilling operation used hardened electronics and redundant communication systems to maintain contact with surface operations. Even with these precautions, equipment failure was common and expensive to repair or replace. The Kola borehole revealed that the deep earth contains conditions far more extreme than surface-based theories had predicted. The discovery of microscopic life forms at depths previously thought to be sterile challenged scientific understanding of where life can exist. The presence of water at depths where geological models suggested only dry rock should exist forced scientists to revise their theories about deep earth processes. These three landmarks, the 2,197-meter Molina Cave, the 4,000-meter Tautona Mine, and the 12,262-meter Kola Superdeep Borehole, represent the absolute limits of where humans have successfully operated or built structures underground. Each depth required increasingly sophisticated technology and represented exponentially greater engineering challenges. The progression from natural caves to mining operations to scientific boreholes shows how human technology has pushed progressively deeper into the earth. Each achievement required solving problems that seemed impossible with previous generations of equipment and techniques. The temperature, pressure, and geological conditions at these depths create environments more hostile than outer space in many ways. Yet even these remarkable achievements pale in comparison to the theoretical depths that modern 2025 technology might reach. The lessons learned from the Kola project and deep mining operations have informed new approaches to deep drilling that could potentially reach even greater depths. However, the extreme conditions encountered at these record-breaking depths reveal that we are approaching fundamental limits imposed by the physics of deep earth environments. Human presence becomes increasingly impractical as we venture deeper underground, and these landmark depths represent the transition point where only our most advanced machines can operate effectively. Where machines take over. At depths beyond 200 meters, the air becomes unbreathable and only autonomous systems can operate effectively. These depths mark the transition where drilling robots, smart measurement while drilling tools, and AI-controlled equipment take complete control of operations. Modern drilling automation systems, like Halliburton's Logix platform integrated with Sequel's Drilltronics, represent the cutting edge of this technology, enabling autonomous directional drilling with automated wellbore hydraulics and dynamic surface drilling rig equipment control. Operators can enhance drilling parameters in real time and accurately position wells with the press of a single button, demonstrating how far automation has advanced in 2025. The integration of artificial intelligence and Internet of Things technologies has revolutionized these deep operations. Smart drilling software platforms feature AI-powered search capabilities and operation optimization recommendations that analyze conditions faster than human operators could process the information. IoT-enabled drilling equipment allows comprehensive real-time data collection, monitoring, and remote control through sensors that track critical parameters including temperature, vibration, torque, and depth. Predictive maintenance, powered by cloud-based analytics, has become essential for maintaining operations at these isolated depths, where equipment failure means permanent loss of expensive machinery. China's Shendetake-1 borehole in the Taklamakan Desert demonstrates the capabilities of modern automated drilling systems. This project reached 10 kilometers deep and serves as a testbed for extreme drilling technologies, providing valuable data on managing high-pressure, high-temperature conditions deep underground. The project relies entirely on automated systems because human operators cannot survive the conditions encountered at these depths. The success of such ultra-deep drilling operations hinges on technological advancements, robust engineering techniques, and precise scientific planning that eliminates human intervention from the drilling process. Advanced drilling equipment operating at these depths includes self-calibrating drill bits that use smart sensors to monitor wear levels and make real-time adjustments to ensure optimal cutting performance. High-performance drill bits featuring nano-coating technology, particularly titanium aluminum nitride coatings, demonstrate remarkable improvements in durability, reduced friction, and enhanced heat resistance under extreme conditions. These smart bits can detect when cutting efficiency drops below optimal thresholds and automatically adjust their operation to maintain performance without stopping the drilling process. Hybrid drilling methods combine traditional mechanical drilling with advanced technologies like laser-assisted drilling and ultrasonic vibration techniques. These approaches prove especially valuable when working with delicate or high-hardness materials that would quickly destroy conventional cutting tools. The automated systems can switch between cutting methods based on real-time analysis of material properties encountered during excavation, making decisions that optimize performance for specific geological conditions. Heat-resistant drilling fluids represent another critical advancement for deep automated operations. These specialized fluids maintain their viscosity under extreme thermal stress exceeding 400 degrees Celsius, conditions that would incapacitate human workers instantly. The fluids must continue functioning properly while carrying rock debris to the surface and cooling drilling equipment that operates continuously for weeks without maintenance breaks. Standard drilling fluids would break down completely under these temperature conditions, making these advanced formulations essential for deep drilling success. Communication systems at these depths require fiber optic cables because radio waves cannot penetrate through hundreds of meters of soil and rock. The cables must withstand enormous soil pressure and potential crushing forces that increase with depth. Signal boosters positioned at regular intervals throughout the vertical cable runs maintain data transmission quality. But communication delays mean that automated systems must operate with greater independence and make critical decisions without real-time human oversight. The structural integrity of boreholes becomes increasingly challenging as automated drilling systems push deeper. Rocks at extreme depths experience stresses that can lead to unexpected fractures and collapses, requiring constant monitoring through automated systems that can respond faster than human operators. The pressure is so intense that solid rock behaves almost like a thick liquid, slowly flowing and deforming over time. Automated support systems must continuously adjust to maintain borehole stability without human intervention. Environmental considerations increasingly influence the development of these automated drilling technologies. Energy-efficient motors with power-saving mechanisms have become standard in modern drilling equipment because power consumption becomes critical when operating hundreds of meters underground. The industry has transitioned toward biodegradable lubricants made from plant-based oils, which offer similar performance levels to traditional petroleum-based products, while being environmentally safer if equipment failures result in spills at these isolated depths. Advanced noise-dampening technologies and vibration control systems make modern automated drilling rigs quieter and more stable, improving equipment longevity and ensuring compliance with environmental regulations. These systems operate without human oversight, automatically adjusting their operation to minimize environmental impact while maintaining drilling efficiency. The vibration control becomes especially important at extreme depths, where excessive vibration can destabilize the surrounding rock formation. Machine learning algorithms analyze soil composition, structural stability, and equipment performance to optimize operations continuously. These systems learn from experience and improve their decision-making capabilities over time without human programming updates. The AI can predict equipment failures days in advance and automatically schedule maintenance operations to prevent costly breakdowns that would be impossible to repair at these depths. The autonomous systems operating at these depths represent the absolute limit of current robotic technology. Communication delays, equipment reliability issues, and environmental challenges compound rapidly as depths increase. Emergency response capabilities become meaningless because conventional rescue equipment cannot reach these depths, and human rescue operations would require specialized equipment costing millions of dollars and taking hours to deploy. Standard drill bits wear down quickly under the high temperatures and stress encountered at these depths, making diamond-impregnated bits essential for sustained operations. Even these advanced bits require continuous monitoring through embedded sensors that track performance and automatically adjust cutting parameters to extend operational life. The extreme conditions push artificial intelligence and robotic systems to their current technological limits, creating operational scenarios that test the boundaries of what machines can accomplish independently. Beyond these machine-dominated depths, we approach territory where even the most advanced automated systems begin to struggle. Yet somehow humans have still managed to create functional spaces in these extreme underground environments. The deepest human-made spaces. The deepest concert ever held underground took place at 1,410 meters in Finland, where the band Agonizer performed in conditions that would challenge even the most advanced sound engineering. This remarkable achievement demonstrates how humans have pushed entertainment venues into depths where the natural acoustic properties create sound experiences impossible to replicate on the surface. The solid rock surrounding these performance spaces eliminates all external noise interference, creating recording studio conditions that cost millions to achieve artificially above ground. Yet even these extraordinary entertainment venues pale in comparison to the operational depths, where humans work daily under the most extreme conditions imaginable. At 4,000 meters underground, the Tautona mine in South Africa represents the absolute limit of human occupation beneath the Earth's surface. This gold mining operation extends so deep that workers must travel the equivalent distance of driving between cities just to reach their work areas. The journey from surface to the deepest working levels takes over an hour using high-speed mining elevators, and workers experience ambient temperatures that regularly exceed 60 degrees Celsius. The mine requires massive refrigeration systems that pump chilled air through kilometers of ventilation shafts to create working conditions that humans can survive. These cooling systems consume enormous amounts of energy and represent one of the largest operational expenses for the mining operation. Workers at 4,000 meters face unique physiological challenges beyond just heat and pressure. The human body responds differently to the atmospheric conditions found at these depths, requiring acclimatization periods similar to high-altitude training. The rock pressure at 4,000 meters creates conditions where tunnel walls can collapse without warning. Mining engineers install extensive support systems using steel beams, concrete reinforcement, and rock bolts that extend deep into surrounding stone. The pressure is so intense that solid rock behaves almost like a thick liquid, slowly flowing and deforming over time. Miners must constantly monitor tunnel integrity because the mountain literally tries to close the excavated spaces. Transportation of materials to 4,000 meters requires specialized equipment capable of handling the extreme conditions. standard construction materials behave differently under the pressure and temperature found at these depths. Steel becomes more brittle, concrete curing processes change, and electronic equipment requires additional protection from the harsh environment.